Okay. 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 Assalamualaikum and a very good evening to all of you again. So so today I just going to start a new chapter regarding combustion. So mainly regarding the theory part. Okay. So next week, inshallah, during our physical class, we will see some examples, inshallah. Okay, so this is the next chapter after the compressor and turbine. Okay, so it's regarding combustion. Okay, so what are we going to see in this chapter is fuel, of course, and air to fuel ratio, heating values, heat combustion, enthalpy, the energy part, and also the regarding flame, okay, adiabatic flame temperature. Okay, wait, I mute my WhatsApp. So first, fuels and combustions. Okay, this one you already know. Fuel is any material that can be burned. Okay, so release thermal energy. So we know that in our, for example, our gas turbine. So we have the combustion part, combustion process. So combustion is a heat exchanger. Okay, so heat exchange during within the combustion chamber, combustion process. So there is a transform of energy from the chemical energy of the chemical product with air. So the combustion process will release thermal energy. So from chemical to thermal. Okay, so when we release the thermal energy, so our fluid, the air plus the fuel will reach increase temperature and pressure, right? So that's why increase in thermal energy before entering the turbine, right? Okay. So most familiar primarily consist of hydrogen and carbon, CH. The C carbon and H hydrogen. So they are called usually as hydrocarbon fuels. So we use the chemical compound CnHm. So depending on the molecule, the number of moles of each of the chemical compound from carbon and hydrogen, right? Okay. So for example, some examples of hydrocarbon fuels like coal, gasoline, natural gas, etc. So they have their own notation. So for example, octane, C8H18. The one that we usually see is methane, CH4. Okay, the chemical compound is written like that. Okay, so this is the part of the process of distillation of the crude oils to form the fuel oil, diesel, kerosene, gasoline, etc. Okay, so this is the energy example of energy contents in each type of fuel. For example, we have gasoline with 31.85 kilojoule per liter here. Okay, so this is examples of fuels that exist that we usually use. Okay, next. Okay, so in order for the combustion process to occur, to happen, we need what we call as oxidizer. Okay, so the oxidizer, a chemical compound which is oxidizer mixed with fuel, our hydrocarbon fuel just now. So the combustion process will occur. So the oxidizer usually that we use is air. Okay, because it contains oxygen. Okay. So we know oxygen with if you have oxygen, air, oxygen, etc. So we can the commercial process can occur. Okay. So in terms of mole or volume basis percentage, normally dry air is composed of around 20% of oxygen, 78% of nitrogen, 0.9% of argon. AR is argon. You can Google, okay, the chemical compound argon, small amounts of argon and a small amounts of carbon dioxide, helium, Ne, I don't remember, nitrogen already, okay, and helium. Okay, so all the chemical compounds, small in small amounts. So the main portion is oxygen and nitrogen. So that's why sometimes we to simplify, okay, to simplify the evaluation of the process, the combustion process, when we want to analyze and we want to evaluate the combustion process, sometimes we just approximate the percentage, around 21% oxygen and 79% of nitrogen. We neglect the small amount of the other chemical compounds. So this is just, if you use like this, 21% oxygen and 79% of nitrogen, means that we just approximately, okay, we simplify it. Actually, it contains, the dry air contains other small amounts of other chemical compounds, okay. So combustion is a chemical. What is combustion? It's a chemical reaction, okay, which where we combine the fuel. The fuel is oxidized, means fuel is combined with the air, dry air, for example. Anything, any means any compound that can be used as oxidization, to be oxidized. Okay, usually contain oxygen, and a large quantity of energy is released. So when we mix the fuel and air, okay, which contain oxygen, so a large amount of energy is released, which is the thermal energy just now. So when we have the thermal energy at high temperature and high pressure, then we can produce power, expand in the turbine, etc. Right? Okay, so for example here, each kilomole of oxygen in air is accompanied by 3.76 kilomole of nitrogen. So this is the approximate number of mole of for air. Okay, so for example, one molecule of air, is around 4.76 kilomole. Okay, the number of mole of one molecule of air. Okay, so for 4.776, if we use this approximation, means if we assume 31% of this 4.76 is contain oxygen and another 79% or 80% contains nitrogen, so the number of mole of oxygen and nitrogen in air will be around approximately this value. So 1 kilomole of oxygen, okay, 21%, equivalent to 21%, and 3.76 kilomole of nitrogen, which is equivalent to 79%. Okay, so that accounts for the total of molecule of air, kilomole, number of kilomole of air. Okay. Okay. And then we see what we call as ignition temperature. Okay, so the fuel must be brought in order for the combustion process to occur. The fuel must be we must ignite the fuel to a certain level of temperature, which is depends on the types of fuel. So the ignition temperature, okay. So the minimum initial temperature in atmospheric air around 260 degree for gasoline, 400 for carbon. So depends on the types of fuel. So means that this fuel, in order will mix out with the oxidization just now, oxidizer, okay, at around this level of temperature. This in what we call as ignition temperature for it, for the fuel to be burned, okay, to for the combustion process to occur. Okay, so it has we must bring the fuel to above this temperature, ignition temperature, that we call as ignition temperature. Okay, so proportion of the fuel and air must be in the proper range. Okay, so each combustion process, it has depends on the number of mole, number of the mass, etc. So actually we need to calculate how much actually portion of fuel and air that we need in order for our combustion to be complete. Okay, so proportion of the fuel and air must be in the proper range for combustion to begin. For example, natural gas does not burn in air in concentration less than 5% or greater than about 50%. Okay, this is just example. It means that for each process, we need to calculate first in order for us to determine whether the combustion process can be completed or not, is enough or not, whether we put enough mass, enough quantity of fuel, etc., actually we need to know how much proportion of the fuel that we need to add, and how much the proportion of the air that we need to add in order for we can produce the products that we want, right? Okay, so in a steady flow combustion process, usually reaction in a reaction chamber or combustion chamber, we have what we call the chemical compound, the fuel, the air, etc. Before the combustion process, we call them, the term that we use is reactants. Means reactants is all the chemical, the fuel, oxygen, etc. before the combustion process. So they are called reactants. And after the combustion process, after finish the combustion process, the chemical compound produced, we call it as products. So reactants is before, products is after. Okay. Okay, this is just example of chemical reaction of hydrogen for water. Hydrogen means, for example, if we have 2 kilogram of hydrogen, we mix it with 16 kilogram of oxygen, then we get the total of H2O, water, right? Okay. So first, of course, we need to do the chemical energy balance. So we know, like for one molecule of hydrogen need to be combined with 1.5, 0.5 molecule of oxygen to get one molecule of H2O. Okay, this is from the chemical equation process. Just have to be balanced, the number of chemical compound before and after. For example, here we have 2, so after we need to have 2. So this is the ideal case, means that this is when this can be done if we have complete combustion. Okay. Later on we see incomplete combustion also. Okay, in a steady flow combustion process, the components that enter the reaction chamber are called reactants, and the components that exit are called products. Okay, before and after the combustion process. Okay, and then one of the most important keyword or point. Okay, one important things that we need to calculate, we need to know in for combustion process is what we call as air fuel ratio, or noted as AF. Okay, so air fuel ratio is the ratio of the mass or the mass flow rate. Okay, mass of air over the mass of fuel. So it's like previously we have seen, we have done the fuel to air ratio, right? In gas turbine, we calculate the fuel to air ratio, the small f, remember the small f. Okay, the small f fuel to air ratio is the ratio of the mass of the fuel over the total mass of the air entering the gas turbine, right? But here air fuel ratio is the opposite. It's just the inverse. Okay, the mass of air over the mass of fuel. The name tell itself. So air to fuel ratio. So air above, fuel below. Okay, so we need to define this air to fuel ratio, or AF. Okay, the ratio of the mass of air needed to burn this amount of fuel. Okay, so the reciprocal, the inverse is fuel air ratio, FA. Okay. So for example, here we have 1 kilogram of fuel and 17 kilogram of air. So the air fuel ratio will be 17. Okay, just 17 over 1. So we get 17, and the total products will be 18 kilogram. Just 1 plus 17. Okay. AF, air fuel ratio, represent the amount of air used per unit mass of fuel during a combustion process. Means that if you want to completely burn 1 kilogram of fuel, we need 17 kilogram of air, something like that. Okay, so we need to know how much uh, 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 air that we need, the quantity, right, to burn the fuel. Okay, next, what we call as complete combustion and incomplete combustion. Okay, complete combustion. Complete combustion is something like ideal combustion process. Okay, so if all the carbon in the fuel, okay, the hydrocarbon fuel just now, if all the carbon in the fuel burns and becomes carbon dioxide as the product, all the hydrogen burns to H2O, and all the sulfur, if any, burns to, means all the carbon transform to carbon dioxide, and all the hydrogen of the hydrocarbon fuel is being transformed to H2O, and all the sulfur, if you have the other small amounts in the air, all the sulfur, if burns to sulfur dioxide, SO2, means that the combustion process is complete. Okay, all the carbon, all the hydrogen is being transformed to carbon dioxide, H2O, SO2, etc. Otherwise, if incomplete combustion, if the combustion products contain any unburned fuel or components such as C, carbon, hydrogen, carbon monoxide, or I forgot this name, or OH, okay? Oxygen and hydrogen. Okay, so means that this is incomplete, means that the reactants that we put before the commercial process, not all the reactants is burned. Okay, so there are still unburned chemical compound at the end of the combustion process, at the end of the reaction. Okay, means not all the chemical compound is being burned, so macam habislah. Okay, so it's incomplete combustion, which is, this is the actual case that normally will occur. Incomplete combustion, complete combustion is like ideal. Okay, incomplete combustion means maybe we didn't put enough air. Okay, maybe not enough time, etc, etc. Okay, so makes the combustion process incomplete. So they left unburned fuel components in the chemical in the products. Okay, reasons for incomplete combustion: insufficient oxygen, insufficient of air, insufficient of mixing in the combustion chamber due to the limited of time, right? Limited of time of contact reaction between fuel and oxygen, and dissociation at high temperature. Dissociation of the molecules of the chemical compounds. Okay, dissociate. Okay, separate at high temperature. Means maybe the temperature is too high, etc. Okay, so this is example, the reactants, the fuel C and the hydrocarbon fuel plus mixed with the air, oxidizer. So you get all the component, okay, carbon dioxide, hydrogen, the balance, the excess balance of oxygen, nitrogen, etc, etc. Okay, so a combustion process is complete if all the combustive component are burned to completion. Okay. Okay, this is just extra note. Oxygen tends to combine with hydrogen than with carbon. Okay, therefore, normally H2O is formed first. Okay, so it left the carbon monoxide, maybe carbon or carbon monoxide that is unburned. Okay, and then we have another term that we call as stoichiometry or theoretical air. So stoichiometry is like theoretical, okay, theoretical air. Okay, what is a stoichiometry or theoretical air? The minimum amount of air needed for the complete combustion of a fuel, also referred to as the chemically correct amount of air or 100% theoretical air. Okay, just now we learned about the complete combustion. So in order for us to get a complete combustion of the reactants, okay, so we need to give enough, sufficient amount of air. So how much is the what is the value of this sufficient amount of air is what sorry is what we call as stoichiometric air or theoretical air. So we need to calculate this first usually before we conduct the combustion process. Normally we need to calculate first the stoichiometric air. We need to know first theoretically how much air that we need to put in order for the combustion process to complete. Okay, the chemically correct. I mean theoretically how much? Okay. And then we also have stoichiometric or theoretical combustion. The ideal combustion process during which a fuel is burned completely with theoretical air. Okay, so if we use the exact amount of air needed for combustion process to complete, then the combustion process is called stoichiometric combustion. Okay, it's just a name of the combustion process. Means that the combustion process is uh, completely burned. Okay, that all the fuel is completely burned. And then excess air. Okay, means the excess, the additional. Okay, the extra. Okay, the amount of air in excess of the stoichiometric amount. Okay, usually expressed in terms of the stoichiometric air as percent excess air or percent theoretical air. Okay, mean the extra air left after the combustion process. And the deficiency of air, if the air is less, this one is extra, this one is less. And then equivalence ratio, okay, the fuel air ratio and fuel air ratio just now. So for example, if we have 50% excess air, means that we put 150% of theoretical air. Means we put more than what we actually need in order for the combustion process to completely, the fuel to be completely burned. And then if you have 200% excess air, means that 300% theoretical air that we put. And then 90% theoretical air means that we put less air, 10% of deficiency. Okay, so if we put enough stoichiometric air or theoretical air, so no unburned fuel, no free oxygen in the products. Okay, so this is example also of a chemical reaction equation of methane CH4 with air. Okay, air that contains oxygen and nitrogen, right? One molecule just now, right? So one molecule of air, so you have oxygen and nitrogen. So the complete combustion will produce carbon dioxide, H2O, and nitrogen. This is complete. So the complete combustion process with no free oxygen in the product is called theoretical combustion. No oxygen left. Okay. And then what else do we have? Predicting the composition of the product is relatively easy when the combustion process is assumed to be complete. Okay. So if we have a complete combustion process, so it's easier for us to calculate all the values at the end. Okay. With actual combustion process, it is impossible to predict the composition of the products on the basis of the mass balance alone. So if the process is incomplete, sometimes it's not really direct. Okay, yeah, it's quite tricky for us, because if it's incomplete combustion, sometimes we don't actually know all the small amounts of chemical compound left in the products, right? The small amounts, carbon monoxide, or what else just now, helium, etc. Right? So sometimes it can be quite tricky to if the combustion is incomplete, for us to determine all the final products. Okay. Then the only alternative we have is to measure the amount of each component in the products directly. Okay, so one type of one method of measurement of the composition of the products is using gas analyzer. Okay, this is the mole fraction example. If you want to calculate the mole fraction of carbon dioxide, the product, okay, of the carbon dioxide. So based on the volume of the carbon dioxide over the total volume of the whole products. Okay. So we have, for example, 0.1 mole of carbon dioxide left. Okay. Next, the energy balance. Okay. Just now we talk about the combustion process itself, the hydrocarbon, the chemical compound, the reactants and the products. Okay. Now we see the energy, which is enthalpy lah. Enthalpy in this case, okay? Enthalpy is energy. Okay, please don't forget about that. So enthalpy in joule or kilojoule per kilogram. So from the energy balance, okay, energy balance, the first law, thermodynamics, etc., etc. Okay, so remember that if we neglect the change in kinetic and potential energy, okay, So the energy balance, wait continue. Okay, so if we neglect the kinetic and potential energy in our energy balance of the combustion process or chemical reaction, okay, so what we have, the energy balance is only the energy, the change of energy regarding the chemical reaction. Okay, so this is the energy balance apply during the combustion process. Okay, so we neglect the potential and kinetic energy. Normally we have, okay, but here we only we have work done, work output, heat transfer, input output, etc. But here we only focus on the combustion process, the chemical reaction. So the change of energy in the system during the chemical reaction is the change of energy of that state plus the change of energy of the chemical process itself. Okay, this is usually the reference state, the initial state or the reference state, and this is the and the change of energy of the combustion process, chemical reaction. Okay, so for example here, the microscopic form of energy of a substance consists of sensible, latent, chemical, and nuclear energy. So all the energies, types of energy involved during this chemical reaction. There is nuclear energy, chemical energy, depends on the fuel that we use, latent energy, sensible energy. Okay, what is latent energy or sensible energy? In simple words, sensible energy is any energy process transformation that involve change in temperature. Okay, for example, like the enthalpy usually involve enthalpy change usually involve change in temperature, right? So there is sensible energy. Okay, increase or decrease of temperature. And then we have latent energy. Latent energy is the opposite of sensible energy. Means that any change of energy that is hidden, okay, not really transparent, not really direct, and the small change of energy, okay. There's also sensible energy when the existing chemical bonds are destroyed and new ones are formed during combustion process. Usually a large amount of sensible energy is absorbed or released. Okay, so it relates with the bonding of the atom within the chemical compound, the hydrocarbon fuel, etc. So the sensible, the thermal energy just now, okay, the thermal energy is released when the chemical bonds of the atoms is being broken. Okay. Okay. Okay, so we have different types of enthalpy, okay, to characterize our combustion process. First one, we have enthalpy of reactions. Okay, so enthalpy of reaction is noted as HR. H is enthalpy, R reaction. The difference between the enthalpy of the products at the specified state and the enthalpy of the reactants at the same state for a complete reaction. Okay, so the difference of the energy, enthalpy of the product and the reactants means before and after. And then enthalpy of combustion, HCE, is the enthalpy of reaction for combustion process. The enthalpy of the combustion process itself, okay? It represents the amount of heat released during the steady flow, okay, of 1 kilogram of fuel when it's burned completely. And then we have the enthalpy of formation, okay. If we want to evaporate or want to condense, okay, the transformation, okay, the amount of energy absorbed or released is the component is formed from stable elements during a steady flow process at a specified state. Okay, all this definition you don't have to remember, okay. Just that later on we just see how can we calculate, okay, the total energy or the total enthalpy, okay. Um, we assign the type of function of a stable value. Okay, usually, okay, for the combustion process, okay, we have what we call as enthalpy of formation at reference point, okay, which is noted this one, okay, HF formation at reference point. Reference points is noted as this symbol with this symbol 0 or O, means this is at a reference point, and the bar here on top is in, means that it is, the enthalpy is in kilomole. Okay, the one that we used previously for gas turbine, etc., we usually use kilojoule per kilogram, right? But here for combustion, usually we will use we will calculate the enthalpy in terms of kilomole because of the atom, molecule, etc., right? The chemical, the chemical equation combustion process. So it's the same. The energy balance is the same. It's just that the enthalpy, the energy is written as per kilomole instead of per kilogram. Okay, previously. So to use the unit kilomole, normally there is a bar on top of the physical properties H enthalpy here. Okay, and the O here or zero here is to characterize, to specify that the form that this enthalpy is at reference state. The reference state is usually at room level, 25 degree, around 25 degree, and at pressure 1 atmosphere, 1 bar. Okay, this is the usual standard reference state. Means the enthalpy of the formation if we have if the molecule, the reactants is at 25 degree and 1 atmosphere, 1 bar. Okay, so for example for carbon dioxide, the enthalpy of formation is negative 3.
Is this constant? 3 minus 393.
Yeah, it depends on the this reference state.
Okay.
At which reference state we have. Okay. Okay, so this is example, 1 kilomole of carbon plus oxygen, so we have carbon dioxide. Okay. Okay, and then heating value. Okay. Heating value, previously we see yeah, in the calculation of gas turbine cycle, we have the heating value. For example, the fuel usually around 40,000. Remember, 43,000, 42,000, 40,500 kilojoule per kilogram. Previously in gas turbine, right? Okay. I have my kid beside me. Okay. The heating value that usually we use in the previously in gas turbine cycle around 40,000, 42,000 kilojoule per kilogram. Yeah, I think 43,000, etc. Okay, now, okay, so here the heating value, the amount of heat released when the fuel is burned completely in a steady flow process, yeah, and the products are returned to the state of the reactants. So actually the heating value is like enthalpy of combustions, HC. It's just that it is the opposite, the sign, positive or negative. So the opposite sign of the enthalpy of combustion. So if you have heating value or if you have enthalpy combustion, so just the opposite sign. So you have the value of the heating value of that process. Okay, this one okay lah. High heating value, low heating value, no need. Okay. Okay, so the first law, the energy balance just now, the first law of thermodynamics. Okay, so for steady flow system, we the enthalpy, the calculation of the energy just now, so will be written, we will have like this. So this is the reference state, the enthalpy of the formation at the reference state, usually 25 degree in 1 atmosphere, plus the change of the enthalpy, the change of the enthalpy of the process. Okay, so if we have the full energy balance, steady flow, energy in, the rate of energy input equals to rate of energy output, remember? So if you have heat transfer, work, etc., so this will be our full energy balance, okay? Usually if we neglect the potential kinetic energy, etc., and we neglect also the heat transfer, work, etc., so we have only this part. Okay, this part, the enthalpy part. Okay, again, can be written also like this. So, the enthalpy of the products, the difference of the enthalpy of the products and the reactants. So we will have Q from the energy balance. We have Q and minus W, etc. etc. What else? Okay, it's the same. So for closed system, okay, for a closed system, okay, so for closed system, the change of energy in the system is equal to energy input and output. So for example, you have the combustion device, the heat exchanger. So if you just focus on the heat exchanger, your case study is the combustion chamber, the heat exchanger of the combustion chamber. So that is your system. So the change of energy within the system, within the combustion chamber, is the energy input, the total energy input minus the total energy out. Okay, in minus out. So that is the change of the energy of that system, of the device. Okay, so that is a closed system that we consider. So the energy we have Q, heat transfer, work, etc. Then it will be equal to U is the internal energy. Okay, again, U is internal energy. Internal energy is usually the energy that relates with pressure and temperature, the thermal energy within the body, within the device. Okay, so U, this internal energy, is actually enthalpy minus PV, the boundary work, pressure and volume. Okay, so so for a closed system, if you consider the closed system, so the energy balance will become like this. Okay, it's just that we rearrange the equation. Okay, okay. Adiabatic flame temperature. Okay, in the limiting case of no heat loss to the surroundings, which is no Q in or Q out. Okay, the temperature of the product reach a maximum, which is called the adiabatic flame or adiabatic combustion temperature. Okay, this is the term that we use, the definition. Adiabatic flame temperature or adiabatic combustion temperature, because the word itself adiabatic is means that no heat exchange within the system, in or out of the system. Adiabatic is like, for example, if you have a thermos, a flask, okay, hot water in a thermos. So it's like the cylinder, the thermos, the wall of the thermos, it's like insulated, right? So it is assumed like adiabatic, means no heat exchange within the surrounding of the thermos. So it's something like that, adiabatic, no heat exchange within the surrounding of the body, the system. Okay. So for example here, if our combustion chamber is insulated, okay, our heat exchanger, the device is insulated, so no heat exchange uh, uh, going out or exiting or absorb, okay, input to the combustion chamber. So it is considered adiabatic. Okay, so the temperature of a combustion chamber becomes maximum when combustion is complete and no heat is lost to the surrounding. So if we have insulation, for example, if we insulated our heat exchanger, the combustion chamber, so no transfer of heat within the device, the combustion chamber, and then during the combustion process, the combustion is complete combustion. So the product reach maximum temperature. the products reach maximum temperature after the complete combustion. Okay, so that maximum temperature is what we call as adiabatic flame temperature. Okay, the T max, the maximum that it can reach. Okay, so adiabatic flame temperature of a fuel depends on the state of the reactants. Okay, the chemical compound, the fuel, the air, etc. before the combustion process, the degree of completion of the reaction, whether the combustion is complete or incomplete, or if it's incomplete, how much percentage that it is nearly completion, okay, and then the amount of air used, okay, the air here to the oxidizer. Okay, for a specified fuel at a specified state burn with air at a specified state. Okay, again the adiabatic flame temperature attains its maximum value when complete combustion occurs with the theoretical amount of air. Okay, the stoichiometric air just now. Okay. Okay, energy conversion. Okay. Okay. The rest here is just to recap back. Okay. Okay. So combustion process, there are three requirements to generate a fire: a source of heat, which is the fuel, and oxidizer. So the mixture, the fuel and oxidizer, is brought to a certain high temperature, the heat, okay, then it can produce the products that we want, okay. So the majority of the fuel contains hydrocarbon, which is compounds that combines hydrogen and carbon atoms. Okay.
One question, ma'am.
Mm-hmm.
Oh, what happens if it is incomplete combustion? As I think we discussed earlier, that if not all the compounds are fully utilized, and anything negative on the engine or effects.
Yeah, it means that we have other emissions, other chemical, small amounts of other chemical compounds produced, right?
Yeah.
So of course there are some how to say disadvantage, right?
Okay.
Yeah, if, that is the emissions part, right? So means that we produce gas, the what carbon monoxide, etc. that maybe cannot be used, the unburned fuels, right? So okay, so carbon forms four bonds in hydrocarbon molecules. Okay, so for example, this one is the C4H10. Okay, so this is the chemical how to say chemical compound. Okay, of the uh, wait, oh,
Those are molecules.
of the molecule. So
Yeah.
I didn't know that amine left. Okay, join us. Okay. Okay, so for example, C4H10 is a butane. Okay, so and then the others lah. Okay. So again, combustion reaction features fuel and oxygen as reactants, and carbon dioxide, water, nitrogen, etc. as the products. So this is for butane. This will be the energy balance. So again, first thing first, before we can evaluate the combustion process, we need to write down the chemical reaction. So just that you need to learn just a simple chemical reaction process, the fuel and the air, and they just need to balance. So means that this is if the combustion is complete. Okay, mean if the combustion is complete, we need 2 mole of butane, 13 mole of oxygen, so it can produce 8 mole of carbon dioxide and 10 of hydrogen, H2O. Okay, so this is in terms of chemical, and then from here we can calculate the air to fuel ratio, etc. and know if whether our whether we can achieve a complete combustion or not. Okay, calorimeter is used to measure the quantity of heat energy. So this one example of a device to measure the quantity of the enthalpy just now, the heat energy, the thermal energy release during combustion reaction. Okay. Okay. And then other definition, exothermic and endothermic. Okay. Exothermic reaction. Okay. Burning a fuel can be compared to water. Okay. When energy is released. Okay. Ener- Energy is released during the chemical reaction. We call the reaction as exothermic reaction. Energy release, exothermic. Okay. Energy produced. So the chemical reaction is called as exothermic reaction. Okay. And then if where is the endothermic? Okay. Between India the chemical composition, the combustion of the fuel will release different amounts of heat energy, of course. Okay, so different types of fuel will release different amounts of heat energy because it has uh, different amount of chemical composition, carbon, hydrogen, etc. So it depends on that. So for example, if we have methane, if you use methane and oxygen, of course, okay. So the energy balance, the chemical equation just now for methane and oxygen will be 1 mole of methane plus 2 mole of oxygen, and then it will release 50.1 kilojoule per gram of energy and produce CO2 plus 1 mole of carbon dioxide plus 2 mole of H2O. Otherwise, for octane, 1 mole. Usually, for the chemical equation, okay, process, we will leave the fuel as 1 mole so that we can directly compare, okay, assimilate. If we have 1 mole of fuel, how much mole of air we need? Okay, so the air to fuel ratio calculation will be direct. 1 mole of fuel equivalent to how many moles of oxygen or air, right? So that's why we have 1 mole of octane. Means in order to completely burn 1 mole of octane, we need 35 over 2 to 12.5 oxygen. Okay, and release 44 of energy difference. And then coal, for example, ethanol, wood, etc. Okay, just now exothermic, the energy release, and then the opposite is energy added, absorbed. Okay, so not all reactions are exothermic. Not all chemical reaction. We are talking about chemical reactions. Not all chemical reaction are exothermic. Okay, some reaction absorb the energy, or energy being heat being added to the chemical reaction, such as photosynthesis, etc. Okay, these are known as endothermic process. So endothermic is heat added to the reactants. Is greater than the heat evolved by formation of products. Okay, so the heat, the addition of heat is more significant. Okay, and then exothermic, the heat added to reactants is less than the heat evolved with the product. So the energy release is more significant, more important. Okay, the energy change at the molecule level. Okay, the bonding between the atom just now. Okay, the energy change are due to the rearrangement of the atoms of the reactants and products. So when the hydrocarbon fuels, the oxidizer mixed with oxidizer is being being brought to a certain level of temperature. So the bonding between the atom of the molecules will be broken. Okay, we dissociate. Okay, separate. Okay, breaking bonds requires energy, whereas forming bonds release energy. Okay, usually this relates with the energy absorbed or energy release. Okay, the breaking and forming of bonds dictates if a reaction will be endothermic or exothermic. Okay, so from the separation or the bonding, the breaking or the forming of the atom, we can predict whether the reaction, the chemical reaction is endothermic or exothermic. Okay, if we break the bonds, we require energy to break the bonds. Usually is from the liquid to gas. Okay, to break the bond, the bond. Okay, to break the bond, we need energy, so that will be endothermic, and the opposite is exothermic. If it takes more energy to break bonds than form new ones, then the reaction is indeterminate overall, etc. etc. Okay. So the bond of energy, okay. So I think we can understand directly to break the bonds of the atom, we need energy because we needs high temperature, okay, high temperature to thermal energy to break the bonds. Any change in reaction, okay. This is an example of a reaction of hydrogen and oxygen. This is not regarding fuel. Okay, so uh, a graphic represent a mix of methane. Wait, do I have another? Okay, uh, a mix of methane and air. Mixture of methane and air in a combustion process. So, for example, at the beginning, the reactants is methane, CH4, and the air. It's not being seen. I think it's the purple one. Should be the purple one. Okay. Okay. So at the end, the blue one. Okay. So at the end, it produce the commercial process produce H2O increase, carbon dioxide increase, some hydrogen, small amount of hydrogen, and small amount of carbon monoxide. Okay, or sometimes we have other species, okay, other formations, other small amounts of formation of other compounds, means that the combustion is incomplete. So we might produce other chemical compounds, carbon monoxide, OH, hydrogen, helium, this is HO2, etc. Other chemical compounds. Okay. Okay. This is I skip this first. For regarding flame, I will share next week regarding flames. We skip this first. Ignition. Okay, so ignition in applications where the combustion process is intermittent or periodic, like internal combustion, ignition process becomes an important topic. Okay, so like we mentioned earlier, the fuel, the hydrocarbon fuel, and the oxidizer, the air, oxygen, needs to be brought to a certain level of temperature depending on the types of fuel. Okay, different types of fuel has different ignition temperature. So that is like a minimum level of temperature in order for the fuel to ignite and mix with the air. Okay, okay. I think the rest is just some example of a chemical uh, equation reaction of the fuel and the air. So if you want to write a chemical equation of the combustion process, so for example, it depends on the how much carbon and hydrogen, hydrocarbon fuel we have, and then this is like formula. Okay, so if you have for example, methane just now is CH4. Okay, so X is 1, H is Y is 4, so you can just write here 1 4. So this is like uh, formula to guide you to have a complete combustion of the fuel in the air. Okay, you don't have, we don't need to remember. If we just if we can write down by on our own and calculate and make sure that all the chemical compounds is balanced, then we don't need to use this. This is just to guide us. Okay. Complete combustion with oxygen. So if we have oxygen, I mean the fuel have C, H, and O. I don't know what type of fuel is this, but example, if the fuel has carbon, hydrogen, and oxygen, so the complete combustion chemical reaction equation will be something like this. Okay. What else? Okay. The F factor lambda. I'm not sure whether we need this. Okay. We can keep it first. Okay. So this lambda. Okay. Okay. This lambda is actually okay. Is F factor. Okay. So is for us to know the theoretical, the stoichiometric value just now. Okay, so depending on the number of mole, n is number of mole of our fuel, our hydrocarbon fuel. Okay, and the reactants and the products. So we can calculate lambda. So lambda is the number of mole of, for example, oxygen, the number of mole of the oxygen that we use over the number of mole of the oxygen at stoichiometric level. Okay. Okay. So this lambda can be inserted in the chemical reaction just now. Okay. You will see short one next week if we need it. Okay. We just get complicated the chemical equation. Okay, I think the rest is more towards example of applications of the fuel, power plant, right? This one power plant example, uh, power plant efficiency, the thermal efficiency, net efficiency from the this is like the gas turbine used in power plant. Example source of other fuel source from coal, peat, etc. Okay. This is all the just data, extra data, the distillation process, ethanol, examples of biofuels, etc., etc. Okay. The rest is more like extra information, data. You can read if you want. Okay. Okay, summary. Okay, I think that's all. Just that the flame part I skipped just now. I try to cover or share a little bit because actually flame itself contains another chapter. So I was trying to at least insert some of it in this chapter. So but I don't really actually haven't finished finalize it yet. So we try to see next week inshallah. Okay. Okay, so I think that's it for this the theoretical part for this chapter. So these are some of the exercise. If you want to take a look at it, basically, in terms of the calculation of the air fuel ratio, the mass flow rate needed, right? Of the fuel, complete combustions, the enthalpy, the adiabatic flame temperature, etc. Okay. So I think that's it from me for this week. Inshallah.
Okay.
Anything you
All
want
right.
to ask or add on?
No, I'm okay. Thank you.
Okay, thank you very much. So I'll see you guys next week, inshallah, physically, as usual at 6:30 p.m. Okay.
Okay. All right. Thank you, doctor.
Okay, terima kasih doktor. Assalamualaikum.
All right.
Salam.
So we're going.